So let's get started today. We are going to start new chapter, chapter 9. And in this chapter, we are going to talk about center of gravity or center of gravity. And also we'll talk about the centroid. In the previous lectures, we'll learn how to deal with distributed loading. We said that in order to deal with distributed loading, we need to convert it to single resultant force. And the single resultant force is going to be located at the center of gravity. So locating the center of gravity is very important in order to know the force that is going to be produced by distributed loading. Also, we say that when we dealt with the beam has a weight, and that weight also is going to be located at the center of gravity. So if you don't know the center of gravity, then you are not going to know how much that body is going to produce in terms of moment and forces and etc. So locating the center of gravity is crucial matter here in statics. Remember when we in chapter 5 we said that if you have complicated body, the center of gravity is going to be given for you. So today we need to know how to locate the center of gravity. So for example, here we have a 3D system. We have X, Y, and Z. We need to know how we can determine the center of gravity or the center of mass for a system of particles. So here we have a system of particles in 3D. We have particle 1, 2, 3, 4, and n. It could be 9 or 10. We have a system of particles. We need to know the center of gravity for that system of particles. So here we are going to consider n particles. We have n particles. And also the weight of the particles is going to be parallel forces. So here we have parallel forces. All the particles are parallel forces. We have force 1, 2, and so on. Also, those weights here, it could be replaced by a single resultant weight. So instead of all of these forces, I can represent it by only one single resultant force. And as you might have guessed it, the resultant force here is going to be referred by WR. So the resultant weight is going to be the summation of the weights here. We already know this. If you are going to take the summation of the forces in y-axis, then you are going to say that WR is going to be represent all these weights here. So now we represented all the system of particles by only one weight. Now we need to know the location of that resultant weight. So for example, if we have particle n, then this one is going to have distance in x and distance in y. That is going to represent the center of gravity for that particle here. Now we represent all these particles by WR, the weight of all of these particles. So now we need to know the location of resultant weight. We are going to have X resultant and Y resultant. And that is the center of gravity for WR. Also, we have ZR. Once I know ZR, XR, and YR, I'm in position in order to write the coordinates of the center of gravity. Since we are dealing with 3D dimension, we are going to have X center of gravity, Y, and Z center of gravity. The point of application of the resultant weight here Here is a point of application. We call this center of gravity, CG. So now how we are going to determine the value of XR, YR, and ZR. In order to do that, we need to take the moment about X in order to know YR, and moment about Y in order to know XR. Then either to take the moment about Y or X in order to know ZR. So I need to take the moment either about X or Y or Z. So for example, those weights is going to produce a moment about Y and about X and about Z. So for example, W1 is going to produce a moment about Y by distance, let's call it X1. And if I'm going to have particle N, then I'm going to have Xn. So if I'm going to multiply that force, here is the line of action. Here is the point of rotation. So this one is the shortest distance, the perpendicular distance. So I'm going to have a rotation moment about Y. So all of these weights here, they are going to produce a moment about Y. Then that moment, it should be equivalent to WR, the resultant force, by also the distance in X. So the moment produced by all of these particles, it should be equivalent to the moment produced by the resultant weight, and the distance here is going to represent the center of gravity in X-axis, XR. So here, XR times WR should equal X1 W1, X2 W2 until Xn Wn. So if I want to know XR, I'm going to solve for XR. Similarly, if I'm going to take the moment about X here, W1 is going to produce a moment about X. This time the distance is going to be Y1. And for Wn, I'm going to have Yn. And the moment that is going to be produced by all of these particles should be equivalent to the moment produced by the resultant time the YR, the center of gravity for the resultant. So again, in order to know YR, we are going to say that the moment produced by the resultant times YR is going to be equivalent to all of the moment produced by the particles here. And the perpendicular distance for that case is going to be in Y direction. So if I want to know the value of Y, I'm going to solve for Y here. Similarly, I can do the same for the ZR. Here we have the system. I can rotate the system by 90 degree. So this one is going to be like that, 90 degree. So in that case, obviously, in order to get the ZR is going to be here. Here is ZR. Then I'm going to take the moment about X. I'm going to take the moment about X. Here I have ZR. All the particles is going to be multiplied by their perpendicular distance. So I'm going to find out that ZRWR is going to equal Z1 W1 until Zn Wn. So now I could say that X represent the center of gravity for the system equals the summation of X hat W. X hat here represent the center of gravity for each particle. So here is going to be X hat 1 W1 plus X hat 2 W2 and so on over the summation of the weights, over the summation of the weight. This one was here. Remember, for the equation of the moment. So summation of the particle WR. If I'm going to determine Y, the center of gravity in the Y-axis for a system is going to be the summation of Y hat W over the summation of the WR. And similarly for the Z-axis. Also, we can determine the center of mass. In order to study the dynamic response or accelerated motion of a body in dynamics, it's very important to locate the center of mass. So in the equation, we are going to substitute W by mg. So instead of W, we are going to put mg. So here we are going to put mg, and here we are going to put mg. G is going to be cancelled with the G here. So now the equation is going to be x is the summation of x hat m over the summation of the m. Similarly, we are going to do that in y and in x. So instead of w, we put mg, and the g here is going to cancel the g there, and I'm going to end up with this equation, and this is the center of mass. And if you are going to deal with a body with equivalent amount of the weight is going to be uniform, in that case the center of gravity is going to be the same as the center of mass. Previously, or in the previous slides, we dealt with a system of particles. We have a number of particles. Now we need to deal with a body. We have a body with the random size. This time also we need to determine the center of gravity. Here we have a rigid body. Rigid body is composed of a system of particles inside it. So in this case, each particle here is going to be represented by differential weight, dW. So now I have a particle, and now I have a rigid body, and that rigid body actually is consist of a number of many particles. We are going to take a small part here. We are going to it's going to be represented by differential weight, very small weight. So instead of the system of particles, now we need to deal with a body. We are going to apply the same principles. So here we don't have a number of particles. Here we have a body, so we are going to take a small part of that body, which is very small, differential weight dW. We are going to take small samples, and then in order to represent the rest parts of the body here, we are going to integrate. We are going to integrate in order to represent the rest parts of that rigid body. So we are going to follow the same principle, except of using the summation. Here we are going to use the integration. So for example, if you want to know the value of x here, the center of gravity for that body here, so the weight, the total weight of the body is going to be located at the center of gravity. So we need to know the value of x, the value of y, and the value of z. For that, we are going to take a small part here, differential weight, and that differential weight is going to have its own x and y and z. Then we are going to integrate in order to represent the whole body. So let's say that we need to know the value of x. We are going to take a moment about y. And then we are going to say that if we are going to integrate dw, the integration of dw represent the weight. The integration of dw represent the weight. If I'm going to integrate dw, is going to give me dw, this quantity represent the weight. Is going to be equal to the dwx, and I'm going to integrate to represent all the rest particles. And for that, I'm going to say that the value of x is going to be the integration of x hat dw over the integration of dw. So now, in the previous slides, when we dealt with a system of particles, we used to have integration. We used to have summation here and summation there. Now we are dealing with a rigid body. We are going to use the integration. That's the difference between a rigid body and the system of particles. So now we can use those equations in order to determine the center of gravity. We are going to use, it's the same concept, whether it's a body or it's a system of particle. In system of particle, we are going to use the summation. In the rigid body, we are going to use the integration. Instead of dw, we could put gamma df. Gamma here represents the specific weight, which is the weight over the volume, and V represent the volume of a body. This one times that one, it gives you the weight. Here we have differential weight, and here we have differential volume. So instead of dw, we could put gamma df, and here also gamma df. So gamma with gamma, they are going to cancel each other. Gamma and gamma is going to cancel each other. I'm going to end up with df, and that is the center of gravity for a volume. If I'm going to take this one and that one. Also, in order to determine the center of mass, instead of gamma, we could put rho g. Rho is the density, which is the mass per volume. So instead of gamma, I could put rho g. If I'm going to put rho g, in that case, we are going to call this center of mass. Center of mass. And also, I have the centroid. When we say that centroid, it represents the geometric center. It depends only on the geometry, which means that it depends on the height, the width, and so on. It has nothing to do with the weight. So the centroid is independent of the weight. It only depends on the body geometry. So when we say that determine the centroid, that means the weight has nothing to do with the body. It's going to be depends only on the geometry. And we have the volume centroid, and we have the area centroid, and we have the line centroid. All of these centroids here are independent of the weight. They only depend on the body geometry. So regarding the volume centroid, like I said here, if we get back here, when we replace the dw with gamma dw, I'm going to cancel gamma with gamma. So in that case, I'm going to end up with the volume centroid. So like you can see here, the x, y, and z depends only on the dimension. Depends on the volume and x dash and y dash and so on. So now the weight has nothing to do with the volume centroid. Similarly, regarding the area centroid, instead of dv, if the dimension in z is the same, I'm going to say that dv equal dA time the dimension in z. And the dimension of z is going to cancel each other. So I'm going to end up with dA. And this is the area centroid. Like you can see here, it depends only on the area and the dimension in x and the dimension in y. Also, we have the line centroid. I have a line. I need to determine the centroid. This one depends only on the line and the dimension in x and the dimension in y. So we have three types of centroid. We have the volume centroid, we have the area centroid, and we have the line centroid. And regarding the line here, the center of gravity, it could be located of the object. So it's not necessary that the center of gravity for a line to be located inside the body. So now let's solve example. We need to determine the area centroid for that triangle here. Here we have x, we have y, we have the width b, we have the height h. We need to determine the distance y. So we need to know the value of y for the area centroid. So if I'm going to have triangle, the centroid is going to be located somewhere here. You know that from physics. You know that if I'm going to deal with triangle, the center of gravity is going to be located about 1/3 of the base. So if I'm going to locate the value of y here, is going to equal 1/3 of the height. You already know this, but here we need to know how they got that value. We are going to use what we have discussed in order to get the value here. So the question is, we need to know that value y. Y represent the center of gravity or the area centroid in the y-axis. Also, we have another one in the x-axis, but here you just want to know the value of y. So in order to do that, we are going to use the formula for the area centroid. And in order to use the area centroid, first we need to develop differential element. Like you can see here, we have a rigid body, so we need to take differential element. The first step needs to be done. So we are going to have a rectangle area with area is dA. We are going to take dA. It's going to have finite length and differential width, and the location is going to be arbitrary position. So I'm going to take differential element at a random distance. Let's call it y hat. So in the problem, we need to know the value of y, but first we need to take differential element dA. dA is going to equal x times dy hat, and it's going to be located at arbitrary position y dash. It could be here or there, it doesn't really matter. Then I'm going to express the dA by the dimension here. So the value of dA is going to be x times dy. Like I said, this one could be there, and still that dimension is going to be x. I don't know the value of x. It could be here or there. And the y hat is random position. It could be here or it could be there. So now we express dA by x times dy. Now I know that I'm going to differentiate. So I need to have either to have constant, or I'm going to have y dimension. I don't want to get x dimension. Okay, so that I'm going to be able to differentiate. So I need to express the value of x in terms of y. In order to do that, I'm going to use the similarity between the triangles. I have that triangle, the bigger one, and I have that smaller one, this one. So this triangle here is similar to that triangle there. So I'm going to say that the value of x here, the width or the base of that triangle over the height of that triangle. The ratio between this one and that one is the same as the ratio between this one and that one. So if this one is x, the distance here is going to be h minus y. So the distance from here to here is h minus y. So I'm going to say that x over h minus y is going to be b here, similar to x, over the height. So that ratio is the same as that ratio. Then I could say that x is b times h minus y over h. And now dA is going to be represented instead of x, I'm going to end up with b over h times h minus y dy. The value of b is constant. The value of h is constant. The value of h again is constant. Y is here. It could be at any distance. And here is the dy. So now I'm ready in order to integrate that part. First, because of the x, I'm not able to integrate. So now I expressed the value of x in terms of y. Now I managed to come up with the area of differential element, this value here. Then I need to know the moment arm. So that differential element is going to produce a moment. So I need to know the value. The value here is y hat. I have the value of y hat. So the dA is going to be multiplied by dy to get the moment about x. So now, this formula, we learned that the y here is the area centroid in y-axis is going to equal the integration of y dash dA over the integration of dA. Integration of the dA is the area of that triangle. So now we have expression for dA, which is here. Y dash or y hat is here, is y hat. So y hat is going to be as it is, while dA is going to be that value here. Instead of dA, I could put this one, but I know the integration of dA is half time b time h. So if I'm going to simplify that formula, I'm going to end up with h over 3. So the value of y is h over 3. So I managed to determine the centroid in y-axis using this formula. Similarly, I'm going to determine the value of x. The value of x is going to be in that direction. I need to take a differential element in that direction, and I'm going to repeat that process again in order to get the value. The value is going to be b over 3. If you are going to try to get the area centroid in x-axis. So now we explained how to determine the centroid, area centroid for triangle. And that result is valid for any shape of triangle. If you have any shape of triangle, you are going to say that the centroid in y-axis is going to equal h over 3. We know that if we have triangle like this one, the centroid in x is going to be b over 3. The centroid in y is going to be h over 3, like we just solved from the previous example. And now we need to discuss the centroid for the common shapes. For if I'm going to have triangle, the centroid in x is going to be b over 3. The centroid in y is going to be h over 3. The area is 1 over 2 times b times h for triangle. If I'm going to deal with rectangle, the centroid in x is going to be b over 2. The centroid in y is going to be h over 2. And the area of rectangle is b times h, the width times the height. Also, if I'm going to have semicircle, like this one here, the area is going to be 1/2 pi r squared. And the centroid in x is going to be r/2 if your reference is here. If your reference is there, the value is going to be 0. And regarding the distance in y is going to be 4r/3 pi. Also, we could deal with quarter circle. The area, of course, is going to be 1/4 because this one represents the area for a whole circle. If you have semicircle, you are going to multiply by half. Here I have quarter circle. This one here represents the area for a circle. In order to know quarter circle, you need to multiply by 1/4. If you are going to deal with quarter circle, if your distance, if your reference is here, this one is x, this one is y, the distance is x is going to be 4r/3 pi. The distance in y is going to be 4r/3 pi. So now we should be familiar with the centroid for the common shapes. I know most of you, they know this by heart. They already memorize those important property. Okay, so these properties is very important for us to memorize them. So next time we are going to deal with composite bodies. In engineering, normally we are going to assemble sections using composite bodies. Composite bodies, that means I'm going to have shapes that is in reality they are simple shapes. So this one here is a composite body, but it consists of rectangles and triangles. Okay, we are going to have a break. Then we are going to get back to talk about the composite body. So if you are going to have any questions regarding what we have discussed, please ask me now.
Doctor?